In this video, we'll take a look at Lewis structures for polyatomic ions. Polyatomic ions, they're ions. They have many atoms, so more than one type of atom in the polyatomic ion, and then they have a charge, maybe like a 1 minus or a 1 plus or a 2 minus. So that's how we identify these as ions. There's a table that lists the common polyatomic ions. Some instructors, they let you use that. That table might look something like this. And you can see we have the different 1 minus, 2 minus, and 3 minus ions, and not very many positive polyatomic ions. So your instructor may let you use this, check with them, but this does give us a list. I do recommend you memorize the most common ones. That'll make chemistry a lot easier. So back to Lewis structures for these polyatomic ions. We'll go through in this video and do 5 different Lewis structures for common polyatomic ions. They'll get a little bit harder as we go through the video. Let's start with the hydroxide ion, OH minus. The first thing we need to do for OH minus, this is called the hydroxide ion, is count the number of electrons. So when we're doing these Lewis structures for polyatomic ions, we first count the number of electrons. So here's a little table that can help us figure out the valence electrons. So let's look at this. We're looking at oxygen, which is right here. So it's in group 6A, sometimes called 16. It has 6 valence electrons. So 6 valence electrons for our oxygen. We'll add to that the hydrogen. Hydrogen right here is in group 1, called 1A, and it has just 1 valence electron. We also need to take into account this charge here. When we have this negative, that's showing that there's an extra electron. Electrons are negative, and so we just have a negative sign here to show there's 1 more valence electron. So we're going to add that in here as well. And 6, 7, 8. So we have 8 total valence electrons here for this OH minus Lewis structure. We normally put the least electronegative element at the center, but we only have 2 elements, so they're just going to go next to each other. There's our oxygen and hydrogen. We have a total of 8 valence electrons for this OH minus here. So we'll start by putting a pair of electrons between these 2 atoms. That'll form our chemical bond. Hydrogen, it only needs 2 valence electrons, so we're done with hydrogen. For the oxygen, we'll put the rest around the oxygen. We have 2, so there's 2, 4, 6, and then 8. And now the oxygen, it has 8 valence electrons, an octet, and it's sharing with the hydrogen. So the hydrogen, it has a full outer shell. So this is the Lewis structure for OH minus. We should put brackets around it though, because we want to show that this is an ion. So we'll put a bracket here and then on the other side. And then we need to write the charge in there, show that it has this minus charge up here. So we'll just write a minus up here, and that's the Lewis structure. Let's try a positive ion. So it's the same process here. We'll count the valence electrons up, so we can use our table here for that. And let's see, we have nitrogen, which is right here, and that's in group 15, sometimes called 5A. That has 5 valence electrons, and remember, hydrogen has the 1 valence electron. We have 4 hydrogens though, multiplied by 4. And before, when we had the negative sign, we added a valence electron. Here, we're going to subtract 1. This positive means it's lost an electron. It's lost a negative charge, makes it positive. So 5 plus 4 is 9 minus 1. So again, we have 8 valence electrons for this NH4 plus polyatomic ion. Let's write the structure. The least electronegative goes at the center, and in this case, hydrogen will always be on the outside. So we'll just put N here in the center, and then 4 hydrogen atoms around it. We have 8 total valence electrons. We'll put valence electrons between atoms to form the chemical bonds. And in this case, we've used all 8 up. Nitrogen has 8 valence electrons, and each hydrogen has 2. So this is the Lewis structure for NH4+. Let's put our brackets around it again. And then since it's this positive ion, we'll write a positive sign after it. So that's the Lewis structure for the polyatomic ion NH4+. Let's do one that's a little bit different. So Cn-, this is the cyanide ion. It has this negative charge here. So this polyatomic ion here, let's write the Lewis structure. Again, it's only 2 things, so we can just put C and N. And then let's count these valence electrons up. Carbon's right here. It's in group 4A, sometimes called 14. It has 4 valence electrons plus the nitrogen, which has 5. And then we have the negative charge, so we'll add 1 more. That's 9 plus 1, so 10 total valence electrons for the polyatomic ion here, the Cn minus. Let's write the structure. We'll start by putting a pair of electrons between the atoms. That forms the chemical bond, and then we go around and we complete the octets on each of the atoms. But we only have 10 valence electrons. So we've used 2, 4, 6, 8, 10, and you can see carbon's fine with an octet. Nitrogen does not have an octet. So with this type of structure, what we can do is we can move some electrons around. Let's move these right here to form a double bond. Why don't we move 2 more up between here to form a triple bond? So now we have 8 around the carbon and 8 around the nitrogen. So this is the Lewis structure for the cyanide ion. I'm going to move these down here for symmetry. And then we need to put our brackets around. And since it's the negative ion, we'll put our negative charge out here. So let's do one that's a little bit more complicated here, and then after that we'll do one more. So this polyatomic ion, this is the nitrate ion, NO3 minus. Let's count the valence electrons up first. Nitrogen has 5, plus oxygen has 6, but we have 3 oxygen atoms, plus this extra electron here. That gives us 18 plus 6, 24 total valence electrons. Since nitrogen is less electronegative than oxygen, we're going to put that in the center, and then let's put oxygen atoms around it here. Move this up a little bit, and we'll start by putting electrons, pairs of electrons between the atoms. We're forming these chemical bonds. We'll then put electrons on the outside atoms, complete their octets. And at this point, we've used 24 valence electrons. All of the oxygens, they have octets. The nitrogen does not, so we're going to have to share some electrons to make a double bond. So let's just choose this one right here. And now we have the double bond here. Everything has 8. Nitrogen has 8, and each of the oxygens, they have 8 valence electrons. So this is a good Lewis structure for NO3 minus. Let's put our brackets around it here, and then we'll add our negative sign outside. You might be asking, does it really matter where we put the double bond? And it does in a way. We have what are called resonance structures. So if instead of having the double bond here, I had it here, that would be considered a resonance structure of the nitrate ion. I could put the double bond here instead of up here. That would be another resonance structure. So there's 3 resonance structures. And in reality, the Lewis structure is kind of an average of all 3. So that's a little bit different from the other structures where we couldn't draw any resonance structures. Let's wrap up with one more, and we'll introduce the idea of formal charge. This is the sulfate ion, SO4 2-. It's a pretty common ion in chemistry. Let's count the valence electrons up, and then we'll do the Lewis structure for the sulfate ion. Let's see what we have. We have sulfur right here, 6 valence electrons, and then oxygen above it, that had 6, but we had 4 oxygen atoms, plus here we have 2 extra electrons. So now we have 24 plus 6, that's 30, plus 2, 32 total valence electrons. Sulfur is less electronegative, so we'll put that in the center, and then we'll put oxygens around it. So we have 32 valence electrons. Let's put pairs between atoms. That'll form that chemical bond. And then we'll go around and complete the octets on the outside. It's a little bit crowded, so I'm going to spread this out some. So we've used 32 valence electrons, and everything has 8. We have 8 here, 8 here. Everything has 8. So this is a pretty good Lewis structure. Let's put our brackets in here so that we can write our negative charge out there and show that this is an ion, and then we'll put our 2- after that. So we have this, and you might think this is a really good Lewis structure, and it's pretty good. It follows our rules. But when we have things like sulfur and these more complicated polyatomic ions, we do need to check the formal charges. So I put a link to a video on the formal charges for sulfur here, and I'll just kind of explain briefly, though, how we use them. Sulfur actually can have more than 8 valence electrons. It can have what's called an expanded octet. So I could have a double bond here, and I'm still using these 32 valence electrons, and because sulfur can have an expanded octet, this is an okay structure. Likewise, I could do that over here. I could form a double bond and we would be okay. We'd have the octet for oxygen, which must follow the octet rule. And sulfur, it has 2, 4, 6, 8, 10, 12. That's okay for sulfur. So how do you know which is the best Lewis structure, or the one that's more likely to occur in nature? We say the more favorable Lewis structure. For that, you use the concept of formal charge. If I calculate the formal charge on each atom here, the oxygens with the single bond, they'll be -1. Here's my other single bond. Everything else will be 0. And that kind of makes sense. We have a negative charge here and a negative charge here. So that's a total of -2. That gives us our ionic charge. It also tells us where the charge is kind of considered to be on which atoms here. That's helpful. When you're calculating formal charges, you'd like them to be as close to 0 as possible, or in the case of polyatomic ions, to add up exactly to the charge on the ion. So if you're in a more advanced chemistry class, when you have Lewis structures that can have these expanded octets or have different structures, and you're trying to choose which is the most favorable, you may need to use formal charges. And there's a video in the description and a card that links to that. So this is the best Lewis structure, the most favorable Lewis structure for the sulfate ion, SO4 2-. And this is Dr. B with a rather long video on drawing Lewis structures for polyatomic ions. Thanks for watching.